In this project, we will simulate the methane gas flow inside an orifice. Orifice is one of the most common devices for measuring mass flow using pressure difference. The simplest orifice model consists of a perforated plate that is perpendicular to the fluid flow path in the desired channel. The operating mechanism of the orifices is such that when the fluid passes through an orifice, its velocity increases due to the reduction of the cross-sectional area of the flow, and according to the law of mass conservation and constant flow, and according to Bernoulli's principle, the velocity increases and the flow pressure decreases. Similarly, when the fluid exits the orifice, the flow velocity decreases again due to the increased cross-sectional area of the flow path, and as a result, the flow pressure increases. Therefore, a certain amount of pressure difference appears on both sides of orifice, which is measured using pressure transmitters and built-in pressure sensors. As a result, the orifice flow meter uses the same amount of pressure difference to calculate the flow rate of the fluid passing through the desired channel. The present model is designed in 3 dimensions using design modeler software. The model corresponds to a channel with 12 inches long and 0.5 inches diameter, with a cross-sectional reduction in the middle to create an orifice with a diameter of 0.25 inches. The meshing of the present project is done using ANSYS meshing software, and the mesh type is structured. Also, the element number is equal to 54,648.
Under the General Setup tab, you can see different buttons from scales to units. By clicking on a scale, a new window will appear showing you the domain extents of your geometry. Also, under the View Length Units section, you can see the default geometry units, which is meter in this project. Also, under the Scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh is designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. By clicking on check button, you will see that under the console tab, the Fluent software will start to check your mesh for any errors. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part.
Now, there are several assumptions taken into account for this project. First, the type of our solver is defined as pressure-based since we are dealing with incompressible flows. Second, we have selected the absolute formulation for velocity. And third, we have selected a steady time study since we didn't want our results to be a function of time. Also, if you click on the viscose model, in the appeared window you can see we have selected the RNG K epsilon model since it is more accurate than the standard model. Now, in order to add a new material to the Fluent software, you have to expand the fluid under the Material section, right-click on it, and then select New. In the appeared window, you either can define a new material by defining its properties yourself, or you can simply click on Fluent Database and select your desired material from the list of available materials in the Fluent software. After adding the methane material into the software, you have to introduce this material to the computational domain. To do that, you have to expand the cells and conditions and then go over fluid and then double click on the methane part. In the appeared window in front of the material name, you have to change it to methane. After double-clicking on the Boundary Conditions button in the Appeared part, if you click on the Inlet boundary, you can see that the type of this boundary is defined as Velocity Inlet. By clicking on Edit button, a new window will appear in which you can change the settings related to this boundary. In the Appeared window, in front of the velocity magnitude, you can see that the value of 2.286 meters per second is defined. Now, if you click on the Outlet boundary, you can see that the type of this boundary is defined as Pressure Outlet. Again, by clicking on Edit button, you can further adjust the settings related to this boundary. In the Appeared window, in front of the gauge pressure, you can see we have entered the value of 0 Pascal, meaning that our fluid flow will exit our computational domain to the atmosphere. And finally, if you select the wall boundary and then click on Edit button, in the Appeared window you can see stationary wall motion along with no slip shear condition are defined for this wall.
After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order upwind and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. After double-clicking on the Controls button, in the middle section of the software window, you can see that new part will appear. In the Appear part, you can see under relaxation factors for different parameters. Now these values are set here by the software automatically. You can change these values, which are between 0 and 1, by yourself for different projects you do. But it is highly recommended that you do not do that, since it may result in divergence.
There are two ways to check that your simulation process have reached convergence or not. Alongside checking the residuals reaching and nearing zero, you may define an arbitrary report over an arbitrary boundary in order to calculate different parameters like pressure, velocity, temperature, and see whether they reach a constant value or not. If yes, it may be a sign that your simulation process have reached convergence. However, you must check the residuals as well. To create such report, you can simply right-click on Report Definitions, go over New, and select one of the options available based on your simulation.
After double-clicking on the Residuals button, a new window will appear. In the Appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than this criterion, it conveys the meaning that that equation has reached convergence. After double-clicking on the Initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the Compute From drop-down list and clicking on one boundary. For example, by clicking on Compute From All Zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software.
And finally, we double click on the Run Calculations button, and then in the Parameters section, we enter the value of number of iteration we want the software to continue solving our project, and then we click on Calculate button. Now, in order to extract a 2D contour, we have to right-click on Surface, go over New, and then select Isosurface. In the appeared window under the surface of constant, select Mesh and then below it select X coordinate. After that, click on Compute button so that the software will calculate the extents of your geometry in X direction. Next, enter the value of ISO values equal to 0 so that a plane will be generated in the middle section of our geometry. After creating the plane, expand the graphics section, go over contours, right-click on it and then select New. In the appeared window under the contours of section, you can select your desired variable. For example, in this slide, we are going to extract the pressure contour. So we'll leave the contours of section to pressure, and then under the surfaces, we deselect all the selected boundaries and select our created plane, which would be the X coordinate. After that, by clicking on Save or Display button, the software will show us the 2D contour. Now in this slide you can easily see the pressure distribution over a plane which is placed in the middle section of our geometry. In this contour you can easily see the pressure drop after the flow passes through the orifice. You can simply extract another contour by changing the contours of section. For example, we change it from pressure to velocity, and then by clicking on Save or Display button, the software will show us the velocity contours. And finally, in this slide, you can see the velocity distribution inside our computational domain. You can obviously see that the velocity value has increased after the flow passes through the orifice.
Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.